Alright, I would like to tell you about my favorite category. It's been my favorite category for the last year or two now. And I think it's a great category. I'll try and tell you why. I will have a lot of the same themes as we've just been hearing about, except I will explicitly want zero divisors. That's one of the good things here. I should say this is joint work. The talk's going to have sort of two halves. The first is going to be very topological, geometrical. The second is going to be quite categorical. That's joint work with many rays from Bowden College. The second half is joint work with Hal, who was here today, and Sean. And we're planning to submit this soon, one of them to QPL, so any feedback is very welcome. I think this is next. Right, so the story that I want to tell you is, I'm going to talk about these Hilbert modules. I'll explain what they are in a minute. They will form a monoidal category, so it's a setting where we can do all of these things that Kevin was talking about. We can do teleportation, duality, and all that kind of stuff. It's very algebraic, but there's also a nice continuous geometric picture to this that I'll try and explain. And using that will characterize what all these algebraic structures are, for example, the Frobenius structures. And then I'll focus on the tensor unit of this thing. So we're saying we really want zero divisors in there, and there's a good reason, because these tensor units, they hide a lot of structure that you might not think about when you think only about the Hilbert space or only about Q-value relations or something. Namely, the whole structure of some sort of base space-time even is in there. That's what I want to talk about. Okay, so there we go. So let's first start with Hilbert spaces. As everybody knows, and maybe not lots of them, but at least it's some sort of comfort food. So Hilbert space is defined to be a set, right, with a C complex module structure on it, so you can multiply with a complex scalar, and it has an inner product whose value is, again, a complex number. Right, they form a nice monoidal category. You can take tensor products of them. As Kevin was saying, you can recover the complex numbers by looking at the endomorphisms of the tensor unit. So this object that plays a special role here, it sort of also plays a special role inside the category. Right? And then all of the kinds of things you look about in categorical quantum mechanics have nice counterparts in the concrete setting of Hilbert spaces. In a sense, that's why they were built that way. So talking about dual objects, for example, will tell you that the object you're looking at is finite dimensional. There's a dagger on this category, so you can flip things around, so we get that for free. And we know precisely what the Frobenius structures are, non-commutatively. So I will talk about non-commutative things as well. Non-commutatively, there will be finite dimensional C-star algebras, and commutatively, it's a special case of choice of orthonormal basis that gets copied. Okay, so that's the category of Hilbert spaces. We know sort of everything about it. Okay. Now, I'm going to sort of vary this special object C here to play the special role. Right? Instead of C, we're going to talk about functions. So here's C. Right? I'm going to add a second dimension to it in a sense. I'm going to take some sort of base space, X. That's going to be fixed. Now, for the rest of the talk, pick your favorite locally compact Hausdorff space. Could be the real line if you like. I'm going to look at functions that to each point of your base space assign some number. Right? So it might be 0. That's why we get zero divisors, but it might be, in general, some sort of arbitrary continuous way of assigning these things. What I'm going to insist upon is that, so space X might not be compact, right? It might be locally compact, that it tails off towards the end. It goes to 0, it vanishes at infinity. So specifically, I want to look at continuous functions from X to C, such that outside of some compact subset, they get as small as you like. Right, so if I take epsilon to be this, then there exists some compact set, namely this one, outside of which the function stays below epsilon in absolute value. Right? This is what I'm going to replace my complex numbers by. So adding this base space dimension. I'm going to insist on locally compact because we want to talk about open subsets later on, but things do become nicer if it's just a compact space. You don't have to talk about this function and infinity thing. Specifically, a thing that will play a small role later on is you can look at functions not that don't vanish in infinity but that are bounded. Right? So there's always below some given line, but they might not tail off. Right? Again, in the compact case, these two things are the same. Okay, that's the base space. Okay, so what is a Hilbert module? It's going to be the objects of my favorite category. Well, so the definition we had of Hilbert Hilbert space was we had a module over the complex numbers with an inner product value in complex numbers. And I'm just going to replace the complex numbers by this second dimension thing. Right, so I'm going to say it's a set where I can add two vectors, if you like. I can multiply a vector by a scalar, but a scalar is now one of these functions here. Right, and it has an inner product. If I take two vectors, and I can take the inner product, it's not going to be a complex number, it's going to be one of these functions again. So at every point of the base space, I get some value in a continuous way. All right, then you can even talk about complete, like you do for Hilbert space, if like every Cauchy sequence converges, because this thing is complete in a nice norm. And don't forget about that. And in the very same way, you can build a monoidal category out of them. So first we were taking tensor products sort of over the base field of complex numbers. Now we're going to take tensor products over this new thing. So it's a bit more abstract. You have to take care of all the details, but it is a fine monoidal category. And the tensor unit of this thing is sort of a designated special object.
Are you considering the tensor product over that as a ring, or?
As a Hilbert module again. So I take an Hilbert module that's typically called E. So I take E and another one F. I take first the algebraic tensor product over here. So I quotient out, I want it to be bilinear, sort of C naught X bilinear and not C bilinear. And then I complete it in a norm. So you take two Hilbert modules, tensor product and algebraically complete, you get a new Hilbert module.
Okay.
And that's going to be the monoidal structure in this category.
And that's different from the tensor product over C0x seen as the general ring. C0x is a ring, right? The one that's
yes, but so that the modules don't have any ring structure yet.
No, the modules wouldn't, but C0x does.
Yes.
So are those the same as ring modules, or are they different from ring modules?
Yes, so when I say algebraic tensor product,
you mean the ring module?
Yes.
Okay.
Okay, so this object is in my category. It plays a special role again. So for example, if I look at the scalars, so now there's this bounded thing instead of the vanishing in infinity, but basically this object is, I can sort of recover it internally by looking at endomorphisms of the tensor unit. Right, so the first half of the talk, I want to talk about these things here. You have to be very careful with these kinds of things, because lots of things you know from a Hilbert space textbook just are plain false now. For example, it's not true that every bounded map has an adjoint. You can't sort of flip things around for free. You have to make sure that some sufficient conditions are verified. And like we heard about objects being a direct sum of something in their orthogonal complement, that's not necessarily true. You have to be careful. So in other words, there's a choice of morphisms to be made here. You can either take the bounded maps, or you can take the adjointable ones. In the second case you get a dagger category, the first case you don't. I'm going to use both. Okay, so let's start looking at what the dual objects might be and what the Frobenius structures might be. Okay, that's the plan for the next 10 minutes. Is that okay with everyone? Yeah, so sorry, the slogan are sort of scalars are not numbers, right? There are things like zero divisors. The scalars sort of hide this whole spatial structure of the base space. Okay. So that was all very algebraic, the way this definition here. Now I'm going to make it a bit more geometric. So I'm going to talk about bundles of Hilbert spaces. So here's my base space X. Right. What is a bundle of Hilbert spaces? Well, it assigns to each point here some fiber. The fiber is an actual honest Hilbert space over the complex numbers. And it sort of varies continuously as the fiber moves. Right. So that means if I define it formally, I get some sort of big topological space. Just topological, I don't know anything else a priori, with some projection down to X, continuous projection. Right? So that's saying if I have a point here, it sort of lives in the fiber over that base point. Such that each fiber is a Hilbert space. But now I can talk about, let's say, the inner product, for example, is an operation on the pullback of this with itself. Right? So each fiber has an inner product, but it's continuous, right? From the pullback to itself to itself. If this is topological, I can say that. Does that make sense? Maybe I should write it down. this bundle. I can make that bundle. And a bundle map is something that makes the triangles commute. So I'm going to say my inner product. Sorry, it's going to be valued in x, so I should do this. Okay, so I want this map here to be continuous. And the same for the addition and the scalar multiplication, etc. That's what I mean when I say operations are continuous. Okay, there's a second thing. So this big space here, the total space has some funny topology on it to make this work. And the topology looks like such. The condition is that for every point in the total space, it will live over some point in the base space. There is a neighborhood in the base space, and there's some little epsilon. Sort of, and I can make, sorry, for every point in the total space, there is a neighborhood in the base space. There's a section over the thing in the base space. So there's a continuous way of choosing points here for everything in the neighborhood. For every epsilon, I can make sort of tube around this local section. Right, so if I sort of horizontally do epsilon and vertically do this neighborhood, I get these kind of square thingies here. I want those to be a neighborhood of the point. So I want the topology of the big space to be sort of built up locally, if you like. And so this is just to give you a feeling for what these things look like. And now there's a beautiful theorem, and it's saying that this algebraic definition and this geometric definition are the exact same thing. So if I take a Hilbert X module as a category, it's equivalent literally as a category to a category of these things. So how does that work? If I have one of these over there, I can look at all the sections. So for every point in the base, I choose a point in the total space over it in a continuous way. It's a section. And I want the section to vanish at infinity again, so it sort of gets smaller and smaller as you go towards the edge. So that's one direction, that's an equivalence. We'll talk about the other direction later. And so I can trade, and this is a monoidal equivalence of monoidal categories. So everything I can do algebraically here, I can also look at sort of geometrically. Okay. So we don't just have sort of one category of Hilbert space, we have a category of Hilbert spaces for each point in the base space. And so vary continuously. Okay, so now we're ready to talk about dual objects, for example. So in the category of Hilbert spaces, a dual object is literally a finite dimensional space. Right, so the definition is I have to have a kappa and a cap that satisfy the snake equations. I think most people have seen this before. So if I think about this bundle perspective, I have an object in my category now, I have one of these bundles. When is it dual? Well, precisely when it's what I'll call finite. So it means not only is every fiber finite dimensional, but sort of it could happen that this fiber is one-dimensional, two-dimensional, three-dimensional, four-dimensional, and sort of grow bigger and bigger. So every fiber is finite. We also want the dimension to be bounded above. We want the supremum of these dimensions to be finite. All right, I have to make for this to be an if this always implies that. To go the other way, I have to assume an annoying little extra thing on my base space, and this power compact, which means every open cover has a locally finite refinement. And basically what that gives you is you can get a partition of unity. So you can sort of add infinitely many things together and still add up to one. So that was the geometric picture. We can also talk about the algebraic picture. Right? When is an object, when is a Hilbert module dualizable? When it's a dagger retract of something of this form. So when it's a retract of something finite dimensional, if you like. This is called finitely presented projective. So this always implies that. This always implies that. But to get from here to here, you need this power compact. If you were in a compact space, things become a lot easier. You don't have to worry about these partitions of unity. So there it's good enough to say every fiber is finite. You don't have to, they're automatically bounded. Here you can just talk about what you might see sort of in a more usual algebraic textbook. So it's spanned by a finite number of elements and it's projective as well. Right, so there's some details, but it sort of matches our intuition. Right, dual objects are sort of finite dimensional like things. Okay, so that's the first step. Because what I really want to talk about is Frobenius structures, and then the Frobenius structure is automatically dual. Right, so we know now if some object E carries some Frobenius structure, at the very least has to be finite in this sense. And so, in the category of Hilbert spaces, only Hilbert spaces over complex numbers, the special dagger Frobenius structures are precisely the finite dimensional C-star algebras. Same kind of thing works here, except now it sort of varies continuously again. So you don't get one C-star algebra, you get one C-star algebra for each point in your base space, and sort of vary continuously. So there's a definition of, here I talk about bundles of Hilbert spaces, very similar way you can do bundles of C-star algebras. Right, so now every finite fiber is a C-star algebra, and the operations like addition and the star and things are continuous. These are hugely interesting because, for example, what you can do is, if your base space is the unit interval from 0, 1, including the endpoints, then you can, the fiber here could be non-commutative, 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 and all of a sudden over 0 it could be commutative. Right? So you can think of this as sort of some parameter like the Planck scale that takes, that at the end of it all of a sudden becomes classical. And so there's a lot of non-trivial stuff going on. It's a point I want to make. Now anyway, with a lot of work, using this geometric algebra equality, you can show that in this category of modules, the specialized Frobenius structures is such a finite bundle of C-star algebras. So for every point in the base space, I choose a finite dimensional C-star algebra, and I have to have that very continuously. And again, I want the dimensions to be bounded. It shouldn't get out of hand as you go towards the edge of your base space. So in a sense, this tells us everything we want to know about Frobenius structures, but we can dig a bit deeper and look at some nice examples. So let's first look at the commutative ones, for example. So in the category of Hilbert spaces, these are just choice of orthonormal basis. Here you can get a lot more funny behavior. So first of all, what you can always do is sort of have a trivial kind of bundle like this. Right, so every point, there's only 2 points above it, and there's no funny topology going on. So we'll call these things trivial bundles. Sorry, let me actually follow the slides. So let me define what a branch covering is, and then I'll talk about commutative Frobenius algebras. So branch covering is a map from some locally compact Hausdorff space to another one, y over x, that's again surjective. It's continuous, it's open, and I want all the fibers to be finite. Right, so these are 3 examples of such things. Here's a trivial one. Here's, it's called a double cover of a circle, so my base space is now a circle. And above each point in the circle, I don't know, let's say this one here, there's a fiber of 2 elements. Right? But, and this is interesting, there's no way of choosing a section. If I start here and I want to go around continuously, then you have to go around twice and not once. So in other words, this category is not well pointed, so the kind of thing with the H-star axiom is going to run into trouble. So that's one non-trivial example. Here's another one. We have a sort of branch point. So here the fibers are one size 1, size 1, size 1, and there all of a sudden it's size 2. Looks as a fine open continuous map. And so that kind of thing can happen. Okay, so that's a branch covering.
Can you be discrete?
Sorry, what is discrete?
The minus 1.
No, they just have the inherited topology from Y. I don't think I know an example where they're not discrete, but in principle, they don't have to be, I think. Unless it falls to follow from there.
Discrete in what sense?
That's a topological space.
So the restriction.
Oh, you mean each, but locally it will not be.
So each of these is just a finite point.
But in the Hilbert space case, for example, it wouldn't, right?
What do you mean by the Hilbert space case?
The bundle that you presented before. The fibers are Hilbert spaces, they're not discrete spaces.
Let me make this point first and then get back to you. So this is just a branch covering of topological spaces, plus the connection to all this Hilbert space stuff. If I have such a thing, I can make first of all the Hilbert C0x module, and it's in fact namely C0y, and in fact it's going to be a commutative special vector Frobenius algebra in there. Right, so I take let's take this one, I take the bundle. I look at continuous functions on here now that tail off towards infinity. Using P, I can make that into a C0x module. I can multiply with a function, multiply a function on here by a function on there. Right, and I can put an inner product on them. And here's where I need the fibers to be finite. Right, so an inner product has to take values in C0x, so it has to say at each point of the base space some complex number. That's the complex number. Right, and the theorem is, so each such thing gives you a special Lagrave Frobenius algebra. Conversely, every special Lagrave Frobenius algebra is of that form. So this thing is a Hilbert CX module. That's what you were asking, right? So here the fibers, if here, look at this point, for example, the fiber of the topological covering is a two-element set. If you look the same thing for the module, the fiber will be a two-dimensional Hilbert space. That will have a topology. But these 2 points also have a topology. That was what Alex was asking, I think. Did I clear it up? Okay. So yeah, let me try and explain how that comes about. So sort of getting the inner product is easy, getting the scalar multiplication is easy. How do you get the Frobenius structure? So the tensor product in this category of Hilbert modules. Here's my object. Tensor product is so completion of the algebraic tensor product over this base ring. So this is the tensor product of those two objects. It happens to be a push out. So if I now use the Gelfand duality that we heard about earlier, get rid of the C naught, that corresponds to a pullback of the spaces. So for example, if I take this cover here, right, the pullback of the spaces will literally be, X is a circle, is S1, will be the things, both pairs that map down to the same element. So it's this subset of the torus. If I painstakingly go out with my pen and paper and write down what that subset is, make a picture, it looks like this. So all the blue and all the red points here are things where, if I sort of take coordinate 1 along here and coordinate 2 around here, the blue points are all the ones where coordinate 1 squared equals coordinate 2 squared. And the point to notice is these two curves are disjoint. Right, so then this is not like they're looped, I can actually take one of them and co-multiply. So in that way, sort of the fact that this has no global sections is not a problem there. Okay. When am I supposed to stop, Ross? Sorry.
You're supposed to stop in 15 minutes.
So just make the point that you have sort of trivial things. So every special Lagrave Frobenius algebra in the category of honest Hilbert spaces gives rise to a special Lagrave Frobenius algebra in the category of Hilbert modules in this way. There's lots of non-trivial ones as well. And these are all commutative. The same goes in a non-commutative case. There's lots of non-trivial ones, but let me not go into this one. I do want to tell you about a beautiful structure theorem that says, so suppose I'm in my category of Hilbert modules. I have some Frobenius structure in there. Right. First of all, you can prove that the thing itself must be a C-star algebra. Right. So then there's if this was a bundle of C-star algebras, if every fiber is a C-star algebra, it turns out that the total thing also has to be a C-star algebra. So specifically, I can talk about its center, which will again be a C-star algebra. So it makes sense to talk about Hilbert modules over that center. Right. Now it turns out that if I look at the Frobenius structure as a Hilbert X module, it's also automatically a Hilbert module over the center, and then turn the center is a Hilbert module over X. And this goes 2 ways. Now, Center is always commutative, like that's how it's defined. This thing has a special property that's called being central. So the center of such a thing is literally the base ring. So this theorem is saying if you want to know about the special Frobenius structures, it's good enough to know about the commutative ones, which we cover completely, right? We know exactly what they are. We have to study the central ones. And this is open as of yet. I don't have a good structure theorem for those. But I think this is a very nice theorem. Right.
Yes.
Yeah, sorry.
I think I missed what central means.
So an algebra is central. So let's say there's an R algebra, R is a ring. It's called central. If you look at the center of A, there will be some subalgebra. That's actually equal to R. So think about n by n matrices, for example.
What's the center?
Sorry, I should have defined that. Maybe that's the set of elements that commute with everything. So if you think about n by n matrices, it's an algebra over complex numbers. What are the matrices, the 2 by 2 matrices that commute with all other matrices? That's only the ones with the identity times some scalar. So that's an example of the central thing. But as soon as you have something like direct product of M2 with itself. Right, this is a fine algebra. This is pairs of 2 by 2 matrices that just compose them multiplied with pointwise. The center of that will be 2-dimensional now. So that's not central. Does that help? Okay, now I want to switch to sort of the second part of the talk, where, so far it was very geometric, now I'm going to talk about some more categorical stuff. And the idea is, so we have this nice category of Hilbert modules over X. Suppose you just give it to me as a category, what can I give you about X, what can I deduce? Where's this spatial structure hidden? It should be somewhere in the tensor unit, right? And this is the way it will come out. So, if you take an arbitrary object, and have a look at a sub-object of it, you can do that in any category. And we're going to say such a thing as idempotent when S tensor S is isomorphic to S tensor that object, the sub-object of. So specifically, if I take this to be the tensor unit, right, I tensor S is isomorphic to S itself. So that's saying S tensor S is isomorphic to S. So those things are called idempotent subunits, or subobjects of the unit, and they're idempotent. So such things. Now in this category of Hilbert modules, we have that these are precisely the open subsets of your base space. So we can recover the open subsets by purely categorical means, a very clean way. I just want to talk about open subunits. That's a good start. Now, some sub-objects are larger than other sub-objects. Right? And we also find this orthograph somehow. So I have a set of open subsets of your base space. And I say something about how they're related to each other. So with this I'm going to need an assumption, but it's a very, very innocent one. I'm going to call my category firm when tensor product of a monic together with another monic is monic. Fair enough. Yeah, shoot.
Is that meant to be S density?
No.
That's actually
This is the right definition.
okay. Then what's the T at the right?
So S and T are, so subunit is something like this, right? Here's the tensor unit.
Yeah.
Is a map like monic like this, a sub-object that happens to be idempotent. So in a sense that is T is another such thing. So always use sort of capital and small thing for sub-objects. That's a T. Yeah, it's true. I said sort of monic times monic is monic. It's slightly weaker than that. It's monic times identity is monic.
Okay.
So this is a very innocent assumption. Basically all categories we looked at will have this, including Hilbert modules. Alright, so here we have our two units, which is sort of open subsets, if you like. One is included in another. If and only if this thing happens. So in other words, not only can I order them sort of by pure categorical means, I can find the intersection of two of them. And the intersection is literally just taking the tensor product. Right, so if you just give me this category of Hilbert modules, I can find the open subsets of X. I can find their structure as a topological space. That's great. And this is not just for Hilbert modules, right? This works for every braided model category with this innocent assumption. So every category you might care to look at in categorical quantum mechanics has this sort of spatial structure hidden inside. Okay, I'm going to talk about restriction for a bit because then I want to use it to do a nice protocol with. So if we have a Hilbert module, let's say we have a Hilbert bundle over some base space X, we have a open subset U of X, and I can just restrict the bundle to only live on U. And that comes down to taking the tensor product with this idempotent subobject. So, and you can do that in any category whatsoever. Start with any category C. You start and you take sort of an open subset, if you like, one of these idempotent subunits. Then I can make a subcategory of things that sort of only live above that subset. Right? That turns out to be not just a monoidal subcategory, it has a tensor product of its own, but a co-reflective one. So you can sort of take any object over the whole base space, sort of restrict it to only live over a sub-piece of it. Anything that only lives over a sub-piece, I can sort of extend by zeros to live on the whole space again. Right, and this map here I'll call restriction to the open subset to this idempotent subunit. Let's get this. And just to show that this is a nice thing to do, right? Some sort of evidence that there's a good theory of these things. Let me show you this universal property. So this is something people do in algebra. They give you a ring with zero divisors. You might want to formally invert those zero divisors. That's what they call localization, to make the ring local. You do the same thing for categories. You give me a category, you give me a bunch of morphisms in it, and you say, can you please make those things invertible, because that would make my life easier. Right, that's what they call localization. And it has this universal property, and I claim restriction, the thing we did on a previous slide, has this universal property. And the universal property is this. We have this functor that sort of restricts. If I have any other functor into any other category that inverts this class morphisms, that makes them invertible. Right? So if I take one of these morphisms here, I look at its image, it becomes an isomorphism there. Then that must factor through this restriction up to a two-cell, ICL two-cell. Right? So that's just to make the point that this restriction is a nice, well-behaved operation. And another point to make the point that this is a nice, well-behaved operation is at the very last class we heard someone talk about braided monads. So this restriction I was just talking about fixes one idempotent subunit, one open subset, and it restricts to that. But we can do this for every open subset. Right? So I have a whole load of these functors. And you can ask how do they fit together. And that turns out to be a braided monad in this sense. So graded monad is, the monad is an endofunctor on your category. Right? It's now sort of graded by some set of labels, say. For the set of labels, I'm going to take my open subsets, my open subunits. And then the monad that comes out is going to be this restriction to the to that open subset. And sort of the graded monad laws say they all behave well together. So that is the case here. So it's a very nice, well-behaved operation. It works in any graded model category. So we can talk about sort of support of a morphism, right? Over which piece of the base space does this live, outside of which is it zero. So the main theorem now of this talk, it's a very paltry one, but it is an important one, is if I have two maps that are composable, one of them sort of lives over some open subset U, the other one lives over some open subset B. And if I can compose them, right, they can only live over the intersection of U and B. It must be 0 elsewhere. Right, and the same for the tensor color. So that's, it's a one-line proof, but let me show you why this is important, and this is my last slide. So far I've talked about this base space as if it were just a space. It was some topological space. Now what happens if it has more structure than just topological space? Suppose it's something like a space-time thing. So I can talk about open subsets of my topological space. If it had something like a space-time, it should have something like a chronological future and a causal future. So they typically draw that like this. Here's a given subset. This is all the things that can happen in the future. So time goes up, space goes left, right. Generally, so you have the chronological future and the causal future. Generally, they're different. If you start with an open subset, they're exactly the same thing. So that's great. We don't have to worry about that. We can model this categorically by just demanding a closure operator, because these future cones will satisfy these properties always. So that's saying, if you give me any idempotent subunit, any sort of open subset, there will be some sort of bigger code that sort of closes it off causally, if you like. So that turns open subsets into open subsets. So the change of view here is I'm not thinking about the base space as a sort of one-dimensional thing anymore, I'm adding this time, if you like. So now it's the whole plate into my base space.
What is a chronological cone supposed to represent, for instance, in the outside space?
Yes. So I wanted to brush this under the rug. So there's this whole difficult theory of differential geometry on Minkowski spacetimes. And they say there exists a a space-like path from one to the other, or a time-like path from one point to the other. It gives you two orderings. And these, I plus, for example, is the set of all points such that there exists a time-like path from something in your given set to that point you're putting in the set.
So we want to call it.
That's null, right? It includes, causal includes the null one and chronological
Yes.
doesn't.
Oh, okay. It's just whether or not you put the.
Whether or not you have line
No.
iteration, so null
So
surfaces in it.
one of them includes the
Right.
edge, sort of, and the other one doesn't.
Yeah.
These, but then they consider all kinds of weird spacetimes where there's a cut in the fabric, and then this might be closed and this might not, stuff like that.
So do you have any idea what, sorry, thank you. Have you got any idea what set of spacetimes this can cover?
As long as you can give it to me in the form of a closure operator on some para-compact, locally compact Hausdorff space, anyone you like. So that includes all possible manifolds.
Manifolds are always very compact.
At least that's typically taken into the definition.
Right.
Would it screw up your definitions if you had exotic things like wormholes?
Well, so far I haven't actually used any of this yet. You might consider putting more structure on. So let me just finish up and say why I want at least this structure. Sorry, was there another question? Yeah. Okay. So now if you restrict, so right, this is an open subset of the base space, right? Here's another open subset that's smaller, so I can now do my restriction operation from here to here. Right? So that's something like propagation now. I can build some entangled pair here, say. I can sort of forward it to Alice. This is Alice's lab, that's sort of the future that she can touch. Right, so restriction, it was this nice clean operation, now has a good sort of space-time meaning. Alright, oops. You can do the same thing for Bob, right? So here I create two entangled particles. I send one to Alice, I send one to Bob. Right? You can try and do your, write down your snake diagram in the cantilever modules over this space-time case now. And then this paltry theorem we had here about the supports restricting is now saying this snake is not actually equal to the identity, it's only equal to the identity on this part here, where they can both, where one can signal to the other. So Bob has to sort of wait for Alice's input before he can do his correction. Yes, sorry, yeah.
What is it elsewhere?
0.
0. No.
Well, and on the edge, it sort of tips off continuously. So this gives a very fine-grained way to talk about, you know, signaling and causality and all that. It's not just you can do it or you can't. There's actually sort of a region, an idempotent subunit where it works. You can see how these regions interact. So that brings me to the last slide. Some points I wanted to emphasize. Let me think what this is. Yes. Sorry?
Think first.
Yes. So let me just sell this to you. This includes all of Jamie's higher quantum theory stuff, but now continuously. You can have a continuum-based space of colored regions. This includes stuff like Stefano-like infinite dimensional things. Right? All the fibers are finite, but if you take them all together, you get very infinite stuff. Skip that. Right, so now we can talk about, you know, space-time teleportation and things. You can talk about other relativistic quantum information theory tasks like summoning. And there's a lot of open questions now without going through this graphically. This is some sort of graphics, but not the kind of graphics with a snake in them, because we sort of merged the two somehow. Thank you. Let me stop there. We don't want to stay all the time.
I guess we have a quick question we could do that, otherwise we can